I'm Andreas Zeller. I'm the author of the Debugging book, and I'm here to present you a new chapter. Since you already have seen our last chapter on reducing inputs, this chapter is very similar in that it is also about reducing. However, we are not talking about reducing an input to a minimum. Instead, we are working on reducing a set of changes to a minimum. So if you have ever worked with others on a project, if you're a student, this may not necessarily be the case, but I can tell you it will certainly be the case once you work in industry, because there are very few projects that you run by yourself. You will be confronted with the fact that all of a sudden your program that still worked yesterday no longer works today. And this is because of some change happening. And this can be a change of yours, but it can also be a change that was made by others and that you just imported. So, and today we are applying delta debugging on these changes in order to figure out which change it was that actually causes your program to fail. There's actually two ways in which you can isolate such changes. And the first way is related to the usage of a version control system. Seriously, if you do not use a version control system for your software, don't even bother going into any kind of automated debugging or even debugging. Fix your version control first for personal use as well as for project use. If you don't use a version control, you have literally lost all control over your over your project and over your coding. And the situation we're in here is we're having a program that comes in 8 versions, V1 up to V8, and version 1 is the one that passes, and version 8 is the one that fails. And you want to know when exactly the program failed, or at which point in time the program started to fail. You could now go through history, V1, V2, V3, V4, linearly, but this is something that is not very efficient, in particular if it's not, as it is in real-world project, if it's not just 8 changes that have been made, but rather say 1,000 changes. If you work at a big company like Google or Facebook, you're having dozens of changes, sometimes per second, to a big piece of software. So we're actually talking about thousands of changes that are being made at the same time to various parts of the infrastructure. Thinking about it, it's actually a miracle that all this stuff works. And so a much better idea here is to proceed by so-called bisecting. That is, and that's very simple. You choose a version that is right in the middle of this history, such as here, V4 or V5. You try out this one, and if it passes, then you go for the interval between the one that passes and the one that fails. You keep on doing this until you narrow down. This is a logarithmic progression until you narrow down the single change that causes the program to fail. If you are using the Git version management system, you are very lucky here, because Git actually allows you to do this bisecting automatically. There is a command in Git that allows you, that actually guides you through this process. This is super neat. Here we have our 8 versions of our remove HTML markup program. The versions are identified with these hashes, which is, well, which is unique, definitely. So there's no way to mistake anything. They're not super convenient to work with, but you can also work with prefixes if needed. And you can now check out individual versions in here and find out that the first version worked and the last version does not work. So this bisecting thing in Git is something that is very simple. You go and do git bisect start at the very beginning. And when you do git bisect start, then you have to say, state which is the good version. You enter in the command line git bisect good. You say my first version is the good one, and the last version is the bad one. And then git bisect immediately tells you what to check out, and it automatically checks out for you the version in the middle, the fourth version, which you would now go and, so this is the version to check, which you can now build and test and see whether it passes or whether it fails. And you can now say, so we're testing this thing, we're just saying git bisect bad in here, and now the situation is v4 failed, and since v1 passed and v4 failed, we are now going to check out v3. That's also something that git automatically does. Git bisect automatically gives you the third version. So you can list this out, you can try this out, and then you find out that this version fails. So git bisect automatically gives you version 2. And with version 2, you can test again. And at this point, you already have found the moment in time when the program failed, because v2 turns out to be failing just as well. And since v1 passed and v2 failed, now you can go for looking at the change. And this is actually something that git bisect in the very last step actually tells you automatically. It even tells you who was the author of this particular change, such that now you can now so you can now run out of your office, knock on the door of the one culprit who is around there, and tell him or her, "Oh boy, what have you done there? This is just horrible." Well, that's not the way it works. What you do instead is what you do instead is you look at what actually was the change that was being made, which you can do using git diff. It's all built in into this is all built in into version control, and this is where you can now check which change it was that actually introduced the change. And here we have it. Here we have one line. This is this line which we're seeing all over again, because this is the one culprit line, which among others was introduced in this very version. And since it was introduced in this very version, well, at this moment, the error was there and the program failed. So this is already pretty cute because, well, because if you have a means to check out whether an error is there or not, you can very quickly process in a guided fashion with git bisect, and this will get you towards the change that causes the program to fail. You can even do better, and that's even cooler, because what you also can do is you can write a short script that actually tests your software, that tests whether the failure is there or not, which we do over here. So this is the script that we're having. We're having a small Python script that simply imports our function and checks whether the error is there or not. And you have 3 different return codes. If the script returns 0, then this means that the error is not there. If the script returns 1, then it fails. And if there is some other error, which is not the error you're looking for, then your script is supposed to return the special value 125. No idea why it's 125. I guess this was simply a value which is not used very often. And with this script, you can entirely automate the entire git bisect process. Because if you have this script, again, you do git bisect start, you say what the good version is, you say what the bad version is, and then you do this special thing, git bisect run, where you actually state the script that is supposed to be executed, which we have here. And if you do this, all of the git bisect stuff is going to happen automatically. Git is going to check out automatically the version, is going to run your script, is going to check out next version, is going to run your script, and it immediately gives you the version that actually fails. And you can look up at the difference that causes the error directly onto your screen. This is amazing. This is probably one of the best debugging tools as it comes to changes ever, because it's so easy to use. And in particular with the scripting form, you just press a button, relax, and let the test script do its glory. In Python, it suffices for us that we simply import the function in question and we do the test. If you do this in other languages, then of course it doesn't simply suffice to check out the source code. You also have to build things. So you probably have to set up appropriate build commands in your script, or do them manually. And since building can take quite a long time, in particular looking at older or newer versions, this is where such a script can be very handy, because you just do git bisect run, press a button, and everything happens automatically. There you go. Go and have a coffee, and 5 minutes later, when all the individual things are being done, then when all the things are being done, that's when you can then look at the failure-inducing change. Here you go. Now, this is still a somewhat simplistic situation, because this assumes that the changes that are being made are so small that you can quickly find out what's going on. So here, actually, all of our changes fit on one screen. In practice, however, you will frequently end up with changes that include dozens or even hundreds of changed lines, or even worse, when people come in and merge patches, big sets of patches that have accumulated in some other branch, and they merge them back. Sometimes this can even be hundreds or thousands of lines that all of a sudden have changed. And there you are, and you know that adding these 1,000 lines to your code causes the failure. Well, there you are. Oh, good. It's good that we now know that it is these 1,000 lines. What do we do next? There's a way to actually narrow this down even further. And the idea is that you can actually break down these changes further into so-called patches. And every single patch, it just changes one single block of lines in your program. And when you have this set of patches, such as over here we are introducing quote equals false, over here we are changing this condition, over here we are changing this condition, over here we are introducing these two lines. These are 4 separate patches, and each of these patches can be applied separately. And the question is there a set in there is there a minimal set in there which actually causes the failure to occur? And this is what we do in the second half of this chapter. We are introducing some mechanisms to actually compute those differences and getting a set of patches back. So here we go and compute the difference using this diff function between two versions, and we get a set of 4 patches, each of these changing one particular location in the source code. And we can actually look at what these patches are doing. Here's the first patch. It introduces this line quote equals false. The second patch changes this condition to have an end not quote, so there's the third patch. And the fourth patch then introduces this C equals quote or C equals quote and tag, which is, as we already know, the failure-inducing line. And we have a function called patch, which actually allows us to apply an arbitrary subset of these patches. If we apply all patches to our original version, we get the new version, but we can also go and apply just a small set of patches. For instance, if we just apply this single patch up here, quote equals false, then we get this line quote equals false, where none of the other changes so far. So now we have patches as first-class objects. We can apply them, and when we have applied them, we can test them. And so we have a set of patches, and in this set of patches, we can find out which one is the failure-inducing patch. And this is something where we can then again go and apply delta debugging. Actually, delta debugging was first introduced on patches. This is also where the name delta debugging comes from, because we're talking about deltas between individual versions of code, a difference between 2 versions of code. Only later was it found out, well, only later did I find out that this actually can generalize to arbitrary parts, and now it's actually, I guess, much more frequently used on input than it would be on code changes. And now what we do is we can invoke a delta debugger on the set of patches, and then we quickly find out that only 2 patches are required to actually cause the failure. Namely, what we have here is our failure-inducing line. This is what causes the failure. And since this refers to the quote variable, we also need to introduce this quote variable in the first place. The conditions that are listed in the other two patches actually are not relevant for the failure to occur. Then we go even further, because delta debugging not only allows us to minimize a set, it can also minimize a difference between two sets. So you have a passing set, which is empty, a failing set that is full. And the question is, can we have a minimal difference between a passing set and a failing set, with this minimal difference actually causing the failure to occur? And this is indeed what we're doing in here. And then what we get as a difference is precisely the one single line in here, because our first patch, quote equals false, does not change, or does not change whether the failure is there or not. The program is still passing. But after we introduce these two lines, the last patch, this is when we get the error. And this is now what we can identify as a cause of the error. Because things are so nice, we're introducing a class called change debugger, in which you can then state which is the first version and which is the last version, and it will automatically compute the differences between the two, and it will automatically compute the minimal difference in here. So you just write with change debugger and you give the two versions, and then you invoke your failing, then you have a test function, which again raises an exception when it fails. So there you go. And then this change debugger has a method called minimal patches, and it will automatically produce a minimal difference between these two versions. So this is something that is very easy to use, again, like Delta Debugger 2. All you need is two versions in here and a test, and it will automatically narrow down all these individual parts. That's already all there is. And what we can learn from that is, if your program fails and you do have an older version that works, this is gold, because then rather than figuring out in these whatever 10,000, 100,000 lines of code that now fail, you can now go for the difference between the version that worked and the old version that worked, the new version that failed, and you can narrow down this difference even automatically, pinpointing those lines that cause the failure. So the question is, can we simply remove those lines that cause the failure? Well, it's technically speaking, yes, but you may also lose some functionality along the way with that. So this yields important hints on where the failure is, but it does not necessarily give you an immediate way to fix the error. Of course, well, removing these things also removes the failure, but the problem is, of course, that this may also remove other functionalities, so you still have to do some homework in order to figure out how best to fix the program. But as a starting point for finding out what is it that went wrong in here, such bisecting or even such delta debugging on changes can give very, very important hints on when exactly a program failed and why it failed.